Since the dawn of humanity, people have looked up at the night sky with wonder and awe, marveling at the vast expanse of stars and galaxies that stretch out before us. For centuries, we have sought to understand the mysteries of the universe, asking questions such as how did it all begin? What is the universe made of? And are we alone in the cosmos? These questions have driven some of the greatest scientific and philosophical minds of all time, leading to groundbreaking discoveries and revolutionary new ideas. From the ancient Greek philosophers who first proposed the idea of heliocentric universe, to the modern-day scientists who study intricacies of quantum mechanics and the nature of dark matter, the search for answers about the universe has never stopped. Welcome to a new episode of Cosmic Mysteries. If you like this content, subscribe. Every week new episode.
The Big Bang Theory is the most widely accepted scientific explanation for the origins of the universe. According to this theory, the universe began as a singularity, an infinitely dense point of matter and energy that rapidly expanded and cooled over billions of years, eventually giving rise to the vast and complex universe we see today. The idea of a universe that had a beginning in time was not always accepted by scientists. In fact, for many centuries, most scientists and philosophers believed that the universe had existed forever, with no beginning or end. This view changed in the early 20th century, with the development of new scientific discoveries and theories. One of the key breakthroughs was the discovery of cosmic microwave background radiation, a faint glow that permeates the universe and is thought to be the afterglow of the Big Bang. This radiation was first detected in the 1960s by two astronomers, Arno Penzias and Robert Wilson, who won the Nobel Prize in Physics in 1978 for their discovery. Another important development was the work of Albert Einstein, who proposed the theory of general relativity in 1915. This theory provided a new understanding of gravity and space-time, and was a crucial step in developing the Big Bang Theory. According to the Big Bang Theory, the universe began as a singularity, an infinitely dense and hot point of matter and energy that rapidly expanded and cooled over billions of years. The expansion was not a uniform process, but rather occurred at different rates in different parts of the universe, leading to the formation of galaxies, stars, and other structures. The evidence for the Big Bang Theory is vast and varied. One key piece of evidence is the cosmic microwave background radiation, which is thought to be the afterglow of the Big Bang. This radiation is distributed evenly throughout the universe, and its temperature is almost exactly the same in all directions. Another piece of evidence is the abundance of light elements in the universe, such as hydrogen and helium. These elements were formed in the first few minutes after the Big Bang, when the universe was still very hot and dense. This theory is supported by observations of the abundance of light elements in the universe, which match the predictions of the Big Bang Theory. Finally, the observed large-scale structure of the universe, including the distribution of galaxies, clusters of galaxies, and superclusters, also supports the Big Bang Theory. These structures are thought to have formed as a result of the initial unevenness in the expansion of the universe, leading to the formation of dense regions where matter accumulated and eventually gave rise to galaxies and other structures. The Big Bang Theory would not be possible without the role of mathematics. From the equations of Albert Einstein's theory of general relativity to the cosmic inflation model proposed by Andre Linde, mathematics has been crucial in helping us understand the origins and evolution of the universe. One of the key mathematical tools used to describe the Big Bang is calculus, which is used to model the behavior of matter and energy in the expanding universe. Another important mathematical concept is the Hubble constant, which describes the rate at which the universe is expanding. More recently, scientists have also used advanced mathematical models to explore the early moments of the universe, such as the first fraction of a second after the Big Bang. These models are based on a combination of quantum mechanics and general relativity, and allow scientists to make predictions about the behavior of the universe during these early moments. The Big Bang Theory is the most widely accepted scientific explanation for the origins of the universe. This theory proposes that the universe began as a singularity, an infinitely dense and hot point of matter and energy that rapidly expanded and cooled over billions of years, eventually giving rise to the complex universe we see today. But what evidence supports this theory? One of the key pieces of evidence for the Big Bang Theory is cosmic microwave background radiation, CMB. This is a faint glow that permeates the entire universe, and is thought to be the afterglow of the Big Bang. The radiation was first detected in the 1960s by two astronomers, Arno Penzias and Robert Wilson, who won the Nobel Prize in Physics in 1978 for their discovery. The CMB is distributed evenly throughout the universe, and its temperature is almost exactly the same in all directions. This is consistent with the idea that the universe began as a singularity, and then rapidly expanded and cooled. As the universe expanded and cooled, the radiation that was initially very hot and dense became cooler and less dense, eventually reaching the temperature of just a few degrees above absolute zero that we observe today. Another important piece of evidence for the Big Bang Theory is the abundance of light elements in the universe. These elements, such as hydrogen and helium, were formed in the first few minutes after the Big Bang, when the universe was still very hot and dense. According to the theory, the high temperatures and densities in the early universe allowed for the fusion of protons and neutrons to create heavier elements. Observations of the abundance of light elements in the universe match the predictions of the Big Bang Theory. The ratios of the abundances of these elements provide a way to measure the density and temperature of the early universe, which can be used to test the predictions of the Big Bang Theory. The observed large-scale structure of the universe is also consistent with the Big Bang Theory. This includes the distribution of galaxies, clusters of galaxies, and superclusters. According to the theory, the universe began as a singularity, which rapidly expanded and cooled. As the universe expanded, the matter and energy in it became less dense, and small variations in density grew over time, eventually leading to the formation of galaxies, clusters, and superclusters. Observations of the large-scale structure of the universe confirm this idea. The distribution of galaxies and clusters of galaxies is not uniform, but rather clustered together in certain regions of the universe. These regions are thought to have formed as a result of the initial unevenness in the expansion of the universe, which led to the formation of dense regions where matter accumulated and eventually gave rise to galaxies and other structures. Another piece of evidence that supports the Big Bang Theory is the redshift of galaxies. This phenomenon occurs when the light from a galaxy is shifted towards longer wavelengths, which is interpreted as an increase in the distance between the observer and the galaxy. The amount of redshift is proportional to the distance between the observer and the galaxy, and this effect has been used to estimate the distances of galaxies from us. Observations of the redshift of galaxies reveal that most galaxies are moving away from us, and that the farther away a galaxy is, the faster it is moving away. Mathematics has played a critical role in the development and testing of the Big Bang Theory. From Einstein's theory of general relativity to the cosmic inflation model, mathematics has provided the framework for understanding the universe's origins and evolution. In this section, we'll explore the role of mathematics in developing and testing the Big Bang Theory. The development of the Big Bang Theory began with Einstein's theory of general relativity, which was first published in 1915. This theory proposed that gravity is the curvature of spacetime caused by the presence of matter and energy. Einstein's theory provided the mathematical framework for understanding the behavior of the universe on large scales, including the dynamics of the expanding universe. One of the key predictions of Einstein's theory is the existence of black holes, which are regions of spacetime where the curvature is so extreme that nothing, not even light, can escape. The theory also predicted that the universe must be either expanding or contracting, and this led to the development of the Big Bang theory. The Friedmann equations. In the 1920s, Alexander Friedmann, a Russian physicist and mathematician, used Einstein's theory of general relativity to develop a set of equations that describe the dynamics of the expanding universe. These equations, known as the Friedmann equations, provided a mathematical framework for understanding the evolution of the universe. The Friedmann equations describe the evolution of the universe in terms of its density, expansion rate, and curvature. They show that the universe must be either expanding or contracting, and that its expansion rate is determined by the amount of matter and energy in it. The equations also predict that the universe must have started out in a hot, dense state, which is consistent with the idea of the Big Bang. The cosmic microwave background radiation, CMB, was discovered in 1964 and is considered one of the most significant pieces of evidence for the Big Bang theory. However, it was not until the 1980s that the CMB was fully understood mathematically. The CMB is a faint glow that permeates the entire universe and is thought to be the afterglow of the Big Bang. The mathematical explanation for the CMB comes from the theory of blackbody radiation, which describes the emission of radiation from a hot object. The CMB is interpreted as the leftover radiation from the hot, dense state of the universe just after the Big Bang. The mathematical analysis of the CMB provides a way to measure the temperature and density of the early universe, which is a critical test of the Big Bang theory. Inflationary cosmology. In the 1980s, the theory of inflationary cosmology was proposed as a modification of the Big Bang theory. The theory of inflation proposes that the universe underwent a period of exponential expansion in the very early stages of its evolution. This theory was developed to explain certain problems with the Big Bang theory, such as the uniformity of the CMB and the observed large-scale structure of the universe. The theory of inflation was first proposed mathematically by Alan Guth, a physicist at MIT. The mathematical framework for inflationary cosmology involves the use of quantum field theory to describe the behavior of the universe in the very early stages of its evolution. The theory predicts that the universe must have undergone a period of exponential expansion, which explains the uniformity of the CMB and the observed large-scale structure of the universe. The Big Bang theory has been tested using a variety of mathematical techniques, including observations of the CMB, the distribution of galaxies, and the redshift of light from distant galaxies. One of the key tests of the Big multiverse hypotheses, exploring the possibility of multiple universes. The concept of the multiverse suggests that our universe may not be the only one in existence. It proposes the existence of multiple universes, each with their own physical laws, constants, and properties. The idea of a multiverse has become increasingly popular in recent years, and has been the subject of much scientific and philosophical debate. In this section, we'll explore the different types of multiverse hypotheses and the evidence that supports them. The many worlds interpretation, MWI, of quantum mechanics is one of the most well-known and controversial multiverse hypotheses. According to this interpretation, every time a quantum event occurs, the universe splits into multiple parallel universes, each corresponding to a different possible outcome. In other words, there is a universe in which the outcome of the quantum event was A, and a separate universe in which the outcome was B, and so on. The MWI was first proposed by physicist Hugh Everett in 1957. At the time, it was met with skepticism and criticism, but it has since gained popularity among some physicists and philosophers. The MWI provides a mathematical framework for understanding the behavior of quantum particles, and has been used to explain a variety of phenomena, including the wave-particle duality and quantum entanglement. Critics of the MWI argue that it is untestable, as we can only observe one outcome of a quantum event. Furthermore, some argue that the theory violates Occam's razor, as it introduces an unnecessary level of complexity. Nevertheless, the MWI remains a popular and intriguing multiverse hypothesis. The inflationary multiverse is another type of multiverse hypothesis, which is based on the idea of cosmic inflation. Cosmic inflation is a period of rapid expansion that is believed to have occurred in the early universe, shortly after the Big Bang. The inflationary multiverse hypothesis proposes that our universe is just one of many bubbles that formed during this period of rapid expansion. According to this hypothesis, the universe expanded so rapidly during inflation that it created multiple separate regions, each with its own set of physical laws and constants. These regions, or bubbles, are believed to be separated from each other by vast distances and may contain their own galaxies, stars, and planets. The inflationary multiverse hypothesis is supported by observations of the cosmic microwave background radiation, which show that the universe is remarkably uniform on large scales. This uniformity is difficult to explain within the context of the Big Bang theory, but it is a natural consequence of the inflationary multiverse hypothesis. Other multiverse hypotheses. In addition to the MWI and the inflationary multiverse, there are several other types of multiverse hypotheses that have been proposed. For example, some theories propose the existence of parallel universes that are physically identical to our own, while others suggest the possibility of universes with different laws of physics. One such theory is the concept of the string landscape, which proposes that there may be an enormous number of possible universes, each with its own unique set of physical laws and constants. This theory is based on the idea that string theory, which is a theoretical framework for describing the behavior of subatomic particles, predicts the existence of a vast number of possible universes. Evidence for the multiverse. The concept of the multiverse is still a matter of debate within the scientific community, and there is currently no direct evidence to support its existence. However, there are several pieces of indirect evidence that have been used to support the idea of a multiverse. Mathematics plays a central role in our understanding of the physical universe. From the laws of motion to the behavior of subatomic particles, mathematics provides a powerful tool for describing and predicting the behavior of the natural world. The success of physics in explaining the behavior of the physical universe is in large part due to the fact that the universe appears to be governed by mathematical laws. The relationship between mathematics and the physical universe has long been a subject of philosophical debate. Some argue that mathematics is a human invention, a set of abstract concepts that we use to describe the world around us. Others argue that mathematics is a fundamental part of the universe, existing independently of human thought. The multiverse hypothesis adds a new layer to this debate. If there are indeed multiple universes with different physical laws and properties, it raises the question of whether mathematics is a universal language that applies across all possible universes, or whether different mathematical structures might be required to describe different universes. The relationship between the multiverse and mathematics is complex and multifaceted. On the one hand, the existence of a multiverse suggests that there may be an infinite variety of mathematical structures, each corresponding to a different universe. This raises the question of whether mathematics is an objective reality, existing independently of human thought, or whether it is a product of human invention. On the other hand, some argue that the existence of a multiverse might actually provide evidence for the universality of mathematics. If mathematical structures are required to describe the behavior of multiple universes, It suggests that mathematics might be a fundamental aspect of the natural world, existing independently of human thought. One of the most intriguing implications of the multiverse hypothesis for mathematics is the idea of the landscape of possibilities. If there are indeed multiple universes with different physical laws and properties, it raises the question of whether there is a mathematical structure that can describe the entire landscape of possibilities. This idea is related to the concept of the string landscape, which proposes that there may be an enormous number of possible universes, each with its own unique set of physical laws and constants. The string landscape is based on the idea that string theory predicts the existence of a vast number of possible universes, each corresponding to a different configuration of the extra dimensions required by the theory. The existence of the string landscape suggests that there may be a vast array of possible mathematical structures, each corresponding to a different universe. Some argue that this implies that mathematics is a product of human invention, a tool that we use to describe the world around us. Others argue that the existence of the string landscape provides evidence for the universality of mathematics, suggesting that there may be a single mathematical structure that can describe the entire landscape of possibilities. Conclusion: the concept of the multiverse has far-reaching implications for our understanding of the universe and its underlying mathematical structure. While the existence of multiple universes is still a matter of debate within the scientific community, the idea of a multiverse raises important questions about the nature of mathematics and its relationship to the physical world. Whether mathematics is an objective reality, existing independently of human thought, or a product of human invention, is a question that has long been debated by philosophers and mathematicians. The existence of a multiverse adds a new layer to this debate, suggesting that there may be an infinite variety of mathematical structures, each corresponding to a different universe.